Okay, today we talked about flow over a bump, and here we have open channel flow. I'm showing the upper left. Open channel flow of depth y1 approaching a bump of height delta. And the question is, what is the depth on top of the bump? So our specific energy equation would say that the flow energy approaching the bump has to be equal to the flow energy on top of the bump plus the elevation of the bed delta. This gives us a cubic for y2. So we have y1 plus q squared over 2g y1 squared. That's our approaching energy. Then we have our flow energy on top of the bump plus the elevation of the bump. We can solve this for y2 as a function of each of the other parameters that are given here, and all those other parameters are given. There are multiple roots. So how do we go about choosing them? Well, we want positive and real. And then we choose either the subcritical or supercritical solution. And to illustrate that, we can look at the specific energy diagram. What else, right? And we have E1 approaching the bump, and then we have E2, where E2 is equal to E1 minus delta. Delta is the amount that the bump goes up. And we go, if this is y1 on the subcritical branch, then our solution at y2 is also on the subcritical branch. Alternatively, if our approach velocity, say y1, I'll call it y1 prime, is on the supercritical branch, then we stay on the supercritical branch and we use y2 prime. So we assess the upstream Froude number, and from that determine which route we select as we go over the bump. Now, we talked at length in class about if delta is such that if delta is greater than E1 minus EC, then the flow needs to adjust. And that adjustment involves gradually varied flow and perhaps a hydraulic jump. GVF for gradually varied flow, possibly a hydraulic jump if we're in the supercritical branch, which we're going to talk more about in our next lecture. The only other thing I want to mention today is flow through a constriction and how that is similar to this case that we've looked at here. So if we go from width W1 to W2, W1 to W2, then because W2 is less than W1, then the flow per width, Q2, is greater than Q1. We can take the same specific energy equation, E1 is equal to E2, and come up with a cubic that says y1 plus q squared over 2g y1 squared is equal to the same expression in the constriction, but now it's q2 squared over 2g y2 squared. This is q1 on the left. Okay, this is 2 y2 squared. Again, cubic for y2. Same idea as in the case of flow over a bump, looking for positive real roots, and we choose the subcritical or the supercritical. Now we need to just think a little bit conceptually about what happens in the specific energy diagram for this case. And I'm just going to sketch the two curves. So here's E1, and then I'll put in blue E2, where E2 is now greater than E1 because the flow per width is increased. Now, if this is E1, which is equal to E2, then we can think about Y1 upstream going to Y2 in the constriction on the subcritical branch. On the supercritical branch, Y1 prime goes to Y2 prime. So again, we choose the subcritical or supercritical route to match upstream conditions. Now the only remaining topic in open channel flow then is to talk about hydraulic jumps, and we're going to do that in detail in the next lecture, and then we can think about how sort of it all fits together.